Hello, good morning. Welcome during our last lecture before Easter. Not last lecture this semester. But before we begin, just to summarize the formal stuff. So the midterm test. So we agreed on midterm tests on 28th, right? 28th April, so in 2 weeks. So next week we have normal lecture right after Easter, and then we have a test. The test will be at the university, room 201, C1. So this large room in C1. I booked it, so it's waiting for you. And yeah, so in 2 weeks, not next week, the 28th of April, the test and the standard rules. So there is still one lecture to go. So more about this already next time.
Sorry, building C1.
Once again.
What building did you mention?
C1.
All right.
So C1, second floor, there is a large room here, but still it's free, so we can take it. We can take it for our test. The room will take place at not the room, but of course the test will start at 11:15. So normally as our lecture ends, will last for 60-70 minutes. So you know very well, you're well experienced about it. You know the rules. Yeah, we go back. Maybe some other questions about it. If no, we move back to the to USB because we were in the middle of interfaces, advanced interfaces, advanced and wireless interfaces in microcontrollers, in embedded systems in general. So from the advanced ones, the USB first. We talked about the USB, the basic rules about the USB, how it works, what are the types of the traffic, there, and the major rules behind, hardware rules behind connecting to the about connecting new devices to the, let's say, network, because it's a tiered star topology, so it's a very special type of the, let's say, network. More is about point-to-point connection. Logical, at least it is point-to-point. But how to use the USB? How to use in practice? So the USB originally was to replace so in the origins, in the beginnings, it was used to replace the UART, or RS-232 interface, so the simple interface that we were talking about during previous semester. So this was to replace this interface. But the USB, as you have already noticed, probably, hopefully, in last week, is significantly more complex. Although we need fewer cables, because just 2 cables, but the complexity is shifted from the hardware, which was the case in UART with these RTS, CTS, DTR lines. So with hardware flow control, in other words, to the software, where we have not only software flow control, but also types of traffic, and also nodes addressing, and in general network layer, not only a link layer, but also a network layer, an application layer above this, so additional. So originally, in the beginnings, where the microcontrollers were missing the USB, special dedicated USB block, the method of utilizing USB in the designs was to use transceivers, USB transceivers. The method is still valid. So still, in case of microcontrollers, in case of the USB usage, for simple microcontrollers, it's still a very good idea, or sometimes it's the only idea, to use the USB transceiver. The only idea, because we have still in microcontrollers multiple USB interface, UART interfaces, while in computers there are none RS-232 ports, not anymore. And so unless you intend to work with very old computer or with some very old machine, you need to be able to convert your signal to the USB format. As I mentioned, on the market we've got a couple of options in case of the transceivers, translating UART to USB. But translation here is of course not that simple. It's not just the physical translation, but the translation is about also changing the frames, changing the frames and reformatting the data. So a small example, one of many chips. So again, if you are more interested in the transceivers, just study the subject in more profoundly. But to show you how it works, one of the chip that I chose, simple FT232R, USB to UART integrated chip made by FTDI company. The FTDI basically is making formal SoCs or ASSPs in greater detail, so application specific standard product. So that's the name of this category, ASSP. So this is the chip. So they did some for their, this is a standard product from their point of view, but it's the very much specialized to very certain applications. Texas Instruments from larger companies is also, for example, delivering this kind of chips. What we can expect inside? So inside, as I mentioned, it's
I'm sorry. Some people are waiting for you to let them in.
Really? Okay, I haven't noticed. Just Igor was waiting. Okay, thanks for the note. So the 232 block diagram consists of a couple of elements. From our perspective, the most important is that everything, so that we can easily convert in this case, UART interface at this side. So there is a UART controller. So some of those D-bus lines are simply RX, DTXD, RTS, and CTS lines, and we can, and it is automatically translated into the USB D+ and D- lines. Moreover, this chip, so again, on the market, you can find various versions. There are versions requiring external clocking, requiring external power supplies. I'm saying about the transceivers requiring even external EEPROM, because in case of USB, we need to sometimes, so some of the things need to be stored there in the EEPROM, the device EEPROM. But fortunately, there exists also versions which are simple single chip solutions. FT232R is somewhere in the middle. It does require external memory, for example, but you can supply directly from the USB bus. The USB bus, the standard one, again, small reminder, there is a requirement of at least 4 volts, 4.35 hundredths of the volts as the VCC value, and with the current capabilities of 0.5 amp. So it's 2 watt. It's slightly more than 2 watts of the available power, which is a lot for this kind of, for supplying this kind of chip. So we can as well use it. And in case of this FT232, in this example sample chip, there is such a possibility that we are using just the ferrite bed, and we supply the FT232. Yeah, small checking. What's the ferrite bed for? here? What role does it play? Simple checking who is awake. What we need ferrite bed for here? What's the sense of it?
So to EMI compliance, the interference attenuation?
Nah, not really. Okay, we could classify first, but it's simpler. The use case is simpler here. It's simpler. What's this for? For who knows why? So from spikes that are coming from the USB, we want to clean the voltage that is coming onto our board, and vice versa. On this schematic, there is missing, of course, one element, one important element. So there is missing a capacitor or capacitors here. There is missing a capacitor here. At this place, so then we have a protection in both directions, so both the spikes, the noises on the voltage are not imported from the USB, from a computer, from a cable, and as well we don't export the noises coming from our PCB board, from our FT232. We don't export them towards the computer. So that's why the ferrite bed is necessary. The ferrite bed, again, it's an inductor, but a special type of inductor which has very high SRF, so self-resonant frequency. Thus, it's suitable for spikes we have in microcontrollers, various kinds of. This option is possible as well. That's the option with individual independent power. Autonomous power is possible, so the option that you can see here in the slide. Yet a small, so here just 5 volts is connected to the reset line, as you can see through this 2 resistors in this example. But to be honest, a small warning from my side about this use case. So that's a bad choice. That's a bad choice from practical point of view. The reason for this is that unless you have a battery operated device, but normally if you disconnect, if you unplug the power supply, in this case, of course, if you unplug the power supply from your PCB, then this voltage will disappear. Then those lines, they will go, they will be zero. They will go high impedance, in fact, but they will go zero. But from the software point of view, so from hardware point of view, nothing will happen. But from the software point of view, the operating system will lose a connection to our device, because formally it will throw it out of the list. So it's about the USB hub, so it throw it out of the list. And then in terminals, for example, this is a problem about getting it back on the list, maybe this way. So from practical point of view, this version is really advisable as the power supply. So you don't need to use the BCC to any other chip. So you can supply the other part of the PCB from your own power supply, autonomous voltage, power voltage supplier. But this interface chip should be supplied directly from the USB 5 volts. That's how it should be done. The next option that we have, so maybe we'll skip this for a moment. The next option that we have in case of a USB today is the use of the USB block, of the USB peripheral inside the microcontroller. So this is option number 2. The option that was that used to be kind of a problem a couple of years back, but fortunately it's not a problem anymore today. That's splendid. The problem was, with this, that USB from the protocol point of view is not only defined on the physical layer, it's not only defined on the link layer, it's not only defined on the network layer, but it's also defined It's also defined on the protocol layer, on the application layer, maybe this way. Which means that we need to, in order to, for our device to be understood by computer, for example, by Linux or Android or Windows or Mac, it has to talk the same language to those operating systems, and this is the application layer that needs to be implemented. So in a few years back, the small problem was with the drivers, with understanding. So because the drivers on the computer are basically used to deliver the same level of understanding of both sides of the computer and of the hardware device. Fortunately, today this became part of the standard. So we've got, in case of USB, there are widely used couple of profiles. And if we implement those profiles on a microcontroller, then our device will be understood properly by a computer. The standard profiles, I will talk about them in a moment. The standard profiles are emulating, so the CDC profile, the standard, the basic one, is emulating the UART. And so in some way, but the good thing is that, but the important thing about the profiles is that besides the hardware part, so the USB block, like we will show it about in a moment. Beside the hardware part, we need some software as well. Some software overlay implemented inside the microcontroller. So what are the major features of the hardware block that we have, that I chose for analysis? So this is the block that you can find in STM32F4. So the features of this block. First of all, full support for the full physical support for the on the go protocol. Yeah, what's this? So there are two important part of this part. Full PHY layer, full PHY. So that's these are two important words here. Full physical layer, interestingly, means that when using USB, we need to know hardware interface chips, like in SPI, like in I2C. Fantastic. So in case of UART, for example, so the competing interface, let's say competing, there was necessary some interfacing chip translating the levels. Here, no. Here we have a full physical layer directly implemented onto the microcontroller. It simplifies the design fantastically, because in fact, what we need to do is we need to just connect microcontroller to USB pins, to D+ and D- lines, plus the grounding. It's done. You can connect power supply, you don't need to, but in general, that's done. That's simple. Second thing about this sequence, second part, the optional on-the-go protocol. In short, because I skipped the slides about the on-the-go protocol. What's this for? On-the-go protocol is used to change the role of the device. In USB, very important is if the device is a host or a peripheral. Host, more complex host, generating tokens, host, taking care about the band, taking care about the allocation or slots of time, allocation of data transfer. While peripheral, very simple, just listening to the host, communicating only with the host. So in case of USB in microcontrollers, sometimes we've got just a USB, and then the USB is a peripheral, a USB block, that it can work as a peripheral. That's usually in smaller cheaper microcontrollers, but in more complete microcontrollers, in largest ones like this STM32F4, we have a choice to switch in the program the USB to work as the host. We can force it to work as a host, or we can switch on the on-the-go functionality, the on-the-go protocol suite, because there are two protocols here that needs to be on a mixed hardware software level, in fact, that are necessary to be implemented. So the host negotiation protocol and session request protocol. In case of this functionality, if we connect a peripheral to our microcontroller, the microcontroller will automatically switch to host, and vice versa. If we connect a host to a microcontroller, then the microcontroller will then work as a peripheral. And this functionality is really dynamically changed with the use of the HNP and SRP protocols, which are implemented in the USB block. Then it is of course configurable, as I mentioned, to work as a peripheral, as a host, and as on the go. Here is one important thing, one important element that we have to stop for a moment by. This is full speed. Reminder from last week, we've got 4 options in case of USB today. So LSFS, HS, and SS. In case of microcontrollers, usually we are here. So this has little sense that this is just 1 megabit per second, not much more. So why to use USB? At this speed, you can use a UART. But we've got full speed. But much more often we've got high speed. So high speed is really rare, and as well we don't have a super speed. So that's beyond the range, beyond the capabilities of a microcontroller. So forget about super speed in microcontrollers. Full speed, we talk about 12 megabits per second, and with high speed 480. So it's a hell of a difference. Yet the high speed, the requirements in the high speed block and the functioning of the high speed block is significantly more complex. And in case of the full speed implementation in microcontrollers, it's very common, and very often we've got MAC plus physical layer implemented for full speed. But for a high speed, a very unpleasant surprise is that we have quite often just MAC implemented. It's changing, it's improving. So there are microcontrollers today on the market that are delivering the high speed as well with physical layer, so that as it is then as simple to use as in case of the full speed mode, where we just need to connect a cable, basically connector and a cable to your microcontroller. Yet still be careful, they are on the market microcontrollers with just high-speed MAC implemented. Then not only you need to implement you need to implement an application layer, so all the profiles, but also you need to implement the physical layer, which is a standalone chip. A small topic off top about the FTDI chips. Most of the chips they do offer, most of the chips that you can buy from them most of the chips are just full speed. So high speed you can buy, but high speed, first of all, what's the sense of the high speed with the UART interface? For this purpose, here. For higher speed versions, so for high speed versions, this interface is not a UART interface usually anymore, but it's at least a SPI interface. But usually it's the dedicated parallel interface. It's dedicated parallel interface, because otherwise getting to 400 megabits per second, impossible. So no chance of UART or SPI delivering that amount of data. So small remark about it, but still you can find high speed as well. But be careful. The standard is the full speed. High speed is still something extra. Okay. The next features. There is a dedicated RAM with FIFO control. The dedicated RAM with the 1.25 kilobytes, maybe not maybe not too much RAM, but still a dedicated FIFO, dedicated for the USB, more data to be transferred. So there is a support for the transferring of so many data. Features like dynamic memory allocation, so the multiple packets held in FIFO as well, supporting this kind of high-speed operations. Current maximum path of not so important. Up to 8 host channels, which means that we can have 8 types of traffic being managed by the host itself, if our device is to be a host. Those channels, we can have even up to 8 interrupt plus isochronous transfer request or bulk request. So up to 8 different devices can connect and can make some transfer. Maybe not too many. So we are not able to build with this controller too large network of devices. But still, it's just a microcontroller. So connecting, it's in my opinion, it's more than enough for the applications in embedded systems. This kind of feature is more than enough. In case of peripheral, so if our device works as a peripheral, we can have, so of course, one control endpoint, so for exchanging the control information, but then we have 3 in endpoints and 3 out endpoints supporting all 3 transfer types. So bulk, interrupted, isochronous transfers, all those transfers are possible. So this is more important here. More important information here, so we can transfer all types of information from our device, although one, for example, type of each channel. So if we have isochronous channel, one isochronous channel in this module. But that's about this module. For dedicated TX FIFOs. So again, the data are split between the FIFOs, and the application can be written in a simpler way. It's like in the CAN, in the case of CAN, and the mailboxes in CAN were as well. The mailboxes can be used by various applications independently, and the scheduler takes care about proper sending of the frames. So formally, the block diagram looks like this one. So we've got just the T plus, D plus, D minus, VBus interface plus this special ID line. So the switching on the go of the functionality is done with the 5th pin, with pin ID. So beside the ground, VBus, D plus, and the minus, there must be a connector with 5 pins, not 4. But then, and the ID has to be set to 0 or 1 to. So then either the device is requested to be a host or a peripheral. The block has dedicated RAM, as mentioned, plus the special USB interrupt to NVIC, going through NVIC to the main controller. In case of on-the-go functionality, it gets a bit more complex. So in general, peripheral is the simplest. But if you want to use it as a standalone host, then we need first of all to have the power distribution element. Remember that if a device is to be a host, then the device has to be able to negotiate and negotiate the current, negotiate various parameters like the address, for example, and type of data traffic, but as well it has to be able to deliver physically power supply on the line. So in order to do this, we need to implement some sort of a power distribution switch that will monitor the current and monitor the current flowing from the VDD to 5 volts. Besides, the VDD then has to be 5 volts, or this element has to boost the voltage to the 5 volts requested on the VBus pin, VBus line of the microcontroller of the USB connector. For the reverse direction, there is we can just have a voltage regulator in this direction that regulates, if we are a peripheral, that regulates the voltage coming from the line, from the bus itself. Important thing about the OTG functionality is this: it's the crystal oscillator. In majority of constructions, there is necessary the crystal oscillator when we use the USB, because the crystal oscillator delivers a stable clocking signal, and in case of USB, we've got asynchronous data transfer, which is synchronized by the tokens. So if we talk about the host functionality, the crystal oscillator is really a must. So there is no an optional oscillator, but the oscillator is a must, of course, if our device supports being a host. If our device is to work as a peripheral, then in some microcontrollers it is possible to use internal clocking, because today the newest USB blocks, they offer a synchronization feature. So they are able to synchronize the internal clock to the tokens coming from the host that is connected, of course, somewhere here. But that's only in some. That's only in some USB blocks, not in all. Definitely not in all blocks, which means that you have to be pretty careful. For the host functionality, the crystal oscillator is a must. Crystal oscillator is a must. Okay. That's it about the USB. So yeah, again, we could try to waste more time on this, but we have to go. So 10 minutes to the break. So still we can start with the second of the complex interfaces that we have available in microcontrollers. The interface, which is known under the name of Ethernet, the interface which revolutionized local area networks. Yeah, the revolution took place in 1980s. In 1980s, that's the time where the revolution was taking place, with the huge implementation scale of this in the beginning pretty simple interface. What was the basic idea? You can see on the slide. So in 1970 something, of course in Palo Alto, of course in California, because I don't know why all interesting computer ideas are coming from that. But still, in Xerox company, they got some lunch breaks, so nice weather, so the lunch took longer. But the people there during this lunch, they thought about this kind of a network connecting this kind of architecture, about the network connecting the computers together. various devices together. So the idea was to use so-called Ether. So they called it Ether. Yeah, you should know at least what Ether is, and what's so funny about the Ether here. And they called it anyway the Ethernet. The Ethernet, because the Ether was to carry all the information coming from stations through network interface controller. Network interface controller. So the translation, so that was to adapt the signals coming from the computers to the standards necessary in the Ether, in the Ethernet. So of course, no Ether here, like in case of Michelson experiment, like Michelson proved, but it is about copper usually, and that was those were the beginnings. That the net was a copper with terminations at both sides. So formally, this interface is again a serial to wire differential interface. So from this point of view, this interface seems similar to CAN. The network structure is not really much different than CAN. Of course, CAN is younger. So if we could look for some similarities, then the CAN is similar to Ethernet and Ethernet to CAN, because the original Ethernet looked like this. The CAN, while the CAN got this resemblance later, then Ethernet is not looking like this anymore. CAN still does. So originally it was designed to be used in local and metropolitan even area networks. In the beginning it was local, yeah. Then it was it proved so. I don't know if it proved so good, but people got so acquainted with this protocol because it was implemented in every building in 1980s and 1990s. That in 1990s it started to be used as a metropolitan area network interface, replacing the other protocols that were used there, like FDDI, for example, or ATM. So sometimes we still have this, or SDH. So sometimes we still have this FDI, ATM, or SDH protocols in the backbone of metropolitan networks, but it's pretty common today that as faster Ethernet is used. Normally it's used for communication between simple devices, computers and servers. So runs depending on the technology. We have CSMA CDUs, and here we have a small difference comparing to the previous interfaces, although this is not far from CAN. So that we have a synchronous data transfer, but the synchronous comes from the clock, which is encoded with the signal. So we don't have any tokens which are synchronizing the network like is the USB. We simply have frames, and the receiver has to synchronize with the transmitter, synchronize within a couple of bytes within the preamble that is there, transmitted over the Ethernet network. Here it's written that the communication, so this interface is used for communication between simple devices, computers and servers. And that's exactly where we need this interface for in case of embedded systems. So today, the Ethernet can be used from embedded systems point of view, from this perspective, in two major application areas. One, I think, pretty native application area is to connect our device, our embedded system, to internet network. So then we are able to exchange data over over internet. So we have Ethernet, and we want an internet. We want an internet here. That's one use case. Use case that is weaker and weaker because of the onset of wireless solution. So this is just wired solution, and in case of Ethernet, we've got wireless solutions. Internet, we have wireless access today, which is simpler to be implemented and easier, and it's is in fact replacing very strong. It's a very strong competition today, and it seems that the Ethernet is losing a bit on this field, because the Ethernet, as you will see in a moment, requires quite a lot of various resources to be implemented. Simply making this application of Ethernet in embedded systems quite often a bit too difficult, so a bit challenging. Second use case for the Ethernet is to use it as a local network, a local high throughput and medium range network. Because the Ethernet has a very, of course, again, it does require some burden to be implemented, but the Ethernet is delivering us much faster communication than CAN and much longer distances than USB. So we talk about 10, 100 and gigabit per second standards, and or faster, because that's also the case, but not used in microcontrollers, at least up to now. At the distances of 100 meters even, or even slightly longer, and as well with some infrastructure network, with some star-shaped network, which makes it really useful in some cases where we need high bit rate at higher distances. So this is another interface from slightly different application field than all the other applications that we were analyzing thus far, so this semester and the previous semester. So as to take a look, each interface is for different use case. Ethernet as well has its own use case. Another example, another smaller field, I would say field number 3 of the Ethernet uses. So why we use the Ethernet is that it's a base of a Profinet. Communication protocol, and the Profinet communication protocol, it's slightly modified Ethernet. In fact, it's the major communication protocol used in the machine industry, for example, today, or in automation, connecting devices between themselves, because we need in automation exactly the features that we get from the Ethernet. So we need the medium range network working at high speed in a noisy environment. And all these features are checked here in the Ethernet hardware. So the third use case, again, use case number 1, internet access. Use case number 2, local, and major use case number 3 of the Ethernet in embedded systems is a base of the Profinet. Good. Let's have a short break. After the break, we'll get back to the next features of the Ethernet. Okay, welcome back after the break. So let's move forward with the Ethernet itself. Next features of the Ethernet, usable features in our application. So it's full duplex or half duplex data transfer. Originally, it was half duplex, and that's still you can still have this kind of network constructed. Yet today, majority of applications is about full duplex data transfer mode. The features are point-to-point or point-to-multipoint data transfer. And again, today usually we have point-to-point data transfer because usually we are using infrastructure today, so kind of switches, for example, or routers to connect. The data rate theoretically very high, so we are very high in up to 40 gigabits per second. Laboratory it's even more, but that's not of our interest. We are interested in much lower bit rates. We talk about 10 or 100 on 1 gigabit options, and for these options still we have, in case of Ethernet, because it's so popular, then we still have a couple of hardware layers that we can use. So we mentioned about CAN being available at fiber as well, or a single wire, but it's rarity. In case of the Ethernet, there are a lot of options available. So we've got a coaxial cable. This type of internet is named 10/2. Then we've got twisted pair, shielded or unshielded twisted pair with the 100 base T and 1000 base T as the names of these interfaces. And then we've got fibers, 100 base F, 1000 base SX for multi-mode fiber, and 1000 base LX for single mode long range fiber. So a couple of options we have in case of the physical layer. The physical layer is not only about speed, to be honest. So it's not only about increasing the clock rate, it's more about as well details about it. The details are, for example, about the protocol used, about the coding used, because in protocols like 10, 100 and gigabit Ethernet, we've got 8-bit 10B. So every 8-bit is coded as 10-bit, 10 gigabit per second. Every 64-bit is coded as 66-bit. So yeah, but these are, to be honest, not very important details. Much more important from our perspective is this picture. Picture showing a layered model of the bottom layer of the MAC itself, of the Ethernet itself, because Ethernet is defined on the MAC, on physical and MAC level, and we've got itself the 802.3 MAC. So this is the Ethernet, only this. So just the frame is basically defined, frame and addressing. Then we've got physical medium independent layer with medium independent interface, and usually in microcontrollers, if we get a microcontroller, then usually we have this. We need to add the MAC client from the top. So of course, the MAC client depends on what we need to do, what we want to do. So we can have situations with IP-TCP and the above layers implemented on top. But physical connections, the physical block that we have, the module, the peripheral that we have in microcontrollers is usually just this. That's not the problem from the top. To be honest, that's something we could expect, that we need IP stack implemented in some way, because on the top it's TCP IP usually, at least in the first use case mentioned just before the break. But the problem is usually exactly this part. So the physical medium dependent layer and medium dependent interface. Why is that problem? Take a look about the signals that are requested to be present in the network. So first of all the devices have to, so we have a synchronous data, so we have a single data transfer line. Because of this, we need to combine clock and data. Combining clock and data is done on various ways, depending on the physical speed, the speed of the link. So for the very ancient 10BASE-T, there was used a Manchester encoding, two versions of Manchester encoding. Still, the clock and data are combined, as you can see here. But that's a pretty ancient version. Much more modern, the version that mainly is used today in embedded systems is 100BASE-T, and in 100BASE-T we've got the MLT3 coded. With the MLT3, the data and clock are combined in such a way that the 3-level logic is used. Take a look, not 2-level logic, but 3-level logic is used. Strange thing about this MLT3 signal is that it has such a shape in order to fulfill one of the important requirements of Ethernet network, so that there is no galvanical link between nodes. They have to be separated, galvanically separated, so no direct connection there is. And this MLT3 signal is able to pass through transformers. That's the advantage. And in case of optical layers, we usually have non-return to zero signals, various kinds of non-return to zero, where this, so this is the encoded together to form the data output signal with clock encoded in the NRZ or NRZI signal. So these dedicated signals require a translating chip between a chip translating frame itself. So the idea of the frame, so the frame, standard Ethernet frame, there you can see on the slide. So it's translating between this frame and the connection, the wire, twisted pair, coax cable, fiber, whatever it is, whichever physical layer is in use. In case of the link layer frame of the Ethernet frame used, this Ethernet frame, there are a couple of important things so it is shared between different standards, as you can see, between 10BASE, 100BASE, 1000BASE, and even 10 gig base, the base frame standards. Yet a couple of interesting things about this frame. First of all the numbers, all the field lengths here are in bytes, not in bits. So I'm saying about with the view of microcontrollers. So first thing is that everything is in bytes. What does it mean? It means that a stupid preamble is 7 bytes long, so it's 56 bits long. Plus start of frame, all this goes to, so I'm thinking about those two fields, it's about 8 bytes or 64 bits. So in some protocols, a whole frame is shorter. Take a look, I2C is shorter than here, just start of frame. Second of all, we've got source and destination address, so both addresses directly at this level, which means that the receiver will have an information where this frame came from. So this is different from CAN or from I2C, well, just the destination address is in the frame. So there must be, the data field must then add the information, add the extra information about that, about this, about the addressing, about the source address. Here we've got the source and destination address already there, with source and destination being both 6 bytes. So at least, again, a substantial value. And then comes the data fields, the landscape, and then comes the data field with the minimum length. Again, going back to Khan, frame can be with no data. It's possible, it can be 0. Here, even if the data field length is 0, then there is a padding done. It has a sense, to be honest, because from one perspective, it's we keep the minimum frame size, so we keep the network busy transferring the data. But yeah, it can be proven. It's one of the feature of the Ethernet interface, is that the longer the frame, the longer maybe the network span. It results from the collision detection mechanism used in this network for currents for accessing the medium. So the longer the frame, the longer is the network span. 46 bytes is for 10 and 100 base. But if I'm not mistaken, for 10 gigabytes, 500 bytes, something like this. So I'm not an expert in this field, to be honest, but it's longer. Yeah, but it's still to keep the frame short. It's to keep the frame long enough for the propagation time, for the data propagates properly between two utmost edges of the network. So for the network span, the data field needs to be at least 46 bytes in the basic or interesting for us interface speed grade. Then the top value, take a look, is 1500 bytes. 1500 bytes, so it's 12,000 bits. The hell and a lot. So it's the fact number 3 important one here is that we really need a dedicated extra memory, because it's 1.5 kilobyte per frame. It may be this frame, maybe this long, maybe shorter, but it may be even 1500 bytes, and it's just one frame. So yeah, in case of microcontroller, if we talk about FIFO, we need to be able to have a few frames so that the microcontroller core is able to deduct the content, deduct the validity of the frame, and so on. And for example, to calculate the CRC, because we've got a 4-byte CRC, this is called CRC 32 here. So we need to be able to calculate the CRC, from all the data. And that's another important fact about the Ethernet interface, because we need, when we have a microcontroller implementation of the Ethernet, we need to be able to generate this CRC, which means that we need to be able, the core itself, or the whole microcontroller needs to be able to do it in a short time, to be able to generate, to calculate the CRC out of at least 60 some bytes, and maybe out of 1,000 bytes or so. This usually means that there is no sense of the Ethernet block in a microcontroller if a CRC block is missing, if a CRC peripheral is missing. Usually it means this, and besides, there is useless Ethernet block is useless without a DMA. So if we can sum it up, so if there is the Ethernet, so there must be a CRC and there must be a DMA available inside the microcontroller. Usually this is the case. So usually it goes together. So usually we have all 3 things implemented and present inside the microcontroller, so that we can construct a fairly fast and efficient Ethernet communication system subsystem. But still may happen that some of these elements are missing, then it's a no-go area. So never try using Ethernet, or be extremely cautious with using Ethernet without either CSC or DMA, or both. Unfortunately, that's not all. Because we need the software layer. Here is what I wanted to show you. We need a software layer, and we need, especially in the use case number 1, we need TCP IP, and then we have 2 options basically. Do everything, 3 options. Three options. So in case of TCP/IP implementation in microcontrollers, option number one, do it by yourself. Do it by self, maybe this way. Do it by self, which means that in option number one, first we need to implement encapsulation of IP frames in TCP in Ethernet data field in Ethernet frames, and then we need to encapsulate TCP or UDP frames in IP data field, so in this information data, and then of course if we want to use some something above the TCP and or UDP, so like HTTP, like FTP, like JSON, for example, like WebSockets, then yeah, we need to implement additional protocols and send them through the TCP or UDP data field, and then it got encapsulated down to Ethernet. You can imagine how much work it is. So the solution number two is to take something more or less ready. So the solution on let's say 2A, is to use kind of lightweight IP. So there is such a TCP/IP stack, which is limited, which has limited capabilities, which you can implement. So so we don't have time to get there to this field, but it's there. So if you want, for example, it's included even in STM32 CubeMX. So it means that you can get the cube, you take the cube and you implement it, and you just configure the lightweight IP and wrap it up around the Ethernet block, around the data field of the Ethernet frame, and should be running, and then you're just adding some content from the mail or web pages point of view. That's solution number 2A, and solution number 2B similar, so yet of course not that simple. So you use GPOS. So you try to implement a general purpose operating system. Yeah, it's a bit humorous, to be honest, of course, because the difficulties in implementing even a simple Linux on embedded systems, microcontroller-based embedded system is significant. So to be frankly, I would go then, instead of 2B, I would go for solution number 1. So still, in case of Ethernet, in case of the first use case, so using the Ethernet in Ethernet connection in Internet, that's what you need to do. If you want to use cases number 2 and 3 of the Ethernet, so the local connections or the Profinet, for Profinet and for local, you will need some additional link layer being implemented. So you need some, not link layer, but network layer, because IP protocol is network layer. You would need some network and application layer. You would need to add them, but of course they will be much simpler than the pretty heavy TCP/IP stack that's not required for the Internet. But again, going back, because this was the top, so this was the things that we need to do above the Ethernet. But unfortunately, and that's really painful, to be honest, is that we need to implement something from the bottom, because we need normally, this is our microcontroller. So yeah, I took the slide from the application note of the transceiver chip. That's why there is some PCI interface, but this is our Ethernet block. So this is MCU plus Ethernet block here, and we've got and the Ethernet block delivers two types of interfaces, so MII and MDIO. These are the standard interfaces for connecting the interfacing chips. And the interfacing chips are theoretically should be simple to be used. So I try to show you the USB interfacing chip, which today requires a power supply, a few configuration pins, and that's done. You configure it through a USB connection. Simple from the USB port side, and or from microcontroller, depending on what you need, but you can choose them. The configuration method works as a Fable. It's that simple. So you can use UART, you can use SPI, you can use I2C, you can use parallel interface. So plenty of options we have with the interface chips. That's in case of USB. Ethernet is more expensive, is more demanding, much more demanding, and the connection diagram is far from being simple. I have it somewhere. Yeah, here is the internals of this particular chip. Although this is just the chip supporting 110 megabits per second. And there are the things happening. So there are the blocks happening inside with the coding, with scrambling, with encoding, with coding to the necessary format, electrical format, and then equalizing, de-equalizing. So all kind of stuff is happening inside together with the auto negotiations, and everything is connected through take a look. An interface having in the optimal version, 7 plus 7 plus 2, so 16 pins. 16, not 2 pins in case of UART or 2 pins in case of I2C. Natural, we talk about much higher data rate. So this interface, this MII interface, it's a semi-parallel interface with the MII line, data line being a 4-bit line. 4-bit line, here it is, data only. Sorry, that's the wrong slide. Anyway, this is the data is going over these 2 lines, 3 lines plus the arrow line, because this is an enable line, clock line. Clock is clocking the 4-bit data, so the nibbles flowing through the controller to and from the controller, because it goes in 2 directions. In general, plenty of pins, plenty of elements that need to be connected, and the worst is this. So that's a connection diagram. Because of this, and because of all the control pins and power supply pins necessary, the connection diagram is far from being simple. Far from being simple. But to be honest, that's not the worst. To be honest, that's not the worst in case of Ethernet. The worst out of the worst is the availability of these PHY chips, of this Ethernet PHY chips. I'm not saying about these problems that we have since 2 years, that there is a lot of availability issues in case of semiconductors, but in case of Ethernet PHY chips, they are so difficult to be accessed. They used to be so difficult to be accessed even before. Then it was cheaper and easier and simple samples to buy a dedicated Ethernet card and dismantle it. So very limited choice on the market of these physical chips. They are available, but really difficult to get. And because of this, the Ethernet is the difficulties of the Ethernet implementation in real applications are pretty significant. Of course, you could ask, and you should ask. Maybe I'm speaking too fast, so that you are not able to interrupt me. But anyway, you should ask there. Why not choose a module? Why not use a dedicated PCB with the Ethernet translator, with the Ethernet interfacing? It is possible. Yeah, it is possible. So you can buy such a module that would interface, that would translate some MII interface to the physical signals of the physical, either electrical or optical signals of the Ethernet. But the cost of this chip is about 10 times higher than the cost of the similar chip translating USB to UART, for example, or to SPI. 10 times or even more. So this is complex solution in general and difficult and expensive. So concluding the Ethernet itself, it is possible. So it is available, for example, like you can see here in Ethernet block in the STM32F4. Still so there are 2 major problems with the implementation. Problem number 1, software, so that we usually need, if we want to connect to internet, usually you need to implement a TCP/IP stack. So either use a ready stack or do it by yourself in a limited version. But much more difficult, and usually from practical point of view, really pain in the ass, if I can say it in this way, is defining the physical chip, because it's really not available. It is really not available. It is really not available. Okay. Anyway, that was not maybe very optimistic, but the world is brutal sometimes, and in case of Ethernet, that's unfortunately the case. Oh, here it has the lightweight IP, so open source TCP/IP stack for embedded systems and used by many manufacturers because it's simplified yet working version, so you can use it. Of course, it doesn't have to be used only with the Ethernet, because we will talk about other communication protocols, wireless ones, in a moment, and those protocols also can be connected sometimes to internet, and this lightweight IP can be used for these protocols in these use cases as well. So it doesn't have to be used with Ethernet, with Ethernet only. And then we switch from the wired protocols to a new group of wireless protocols. Why are we doing this? For two reasons. Reason number one is that the most important one is that the embedded systems today, the customers want to pay for wireless access. The customers want to pay for wireless access and for no cables. So this is reason number one. And reason number two, coming from the reason number one, in fact, is that if the customers want to pay for this, the silicon vendors are delivering chips which can be used for this purpose. And today, even we have the situations where the chips are included, the peripherals, the wireless peripherals are included in various options, various versions inside the microcontroller, and they function as a peripheral. And thanks to this, we've got some options about wireless connection today in embedded systems. Options not requiring very complex hardware. So I would put it even this way: thanks to the implementation of wireless blocks inside, it's usually about a few components that need to be added to the single chip microcontroller for everything to get a wireless connectivity. On the market, in fact, there are a lot of standards, like in case of wired solutions, that's with wireless communication, data communication. We've got plenty of standards and plenty non-standard solutions, to be honest. So in general, we've got the main problem is bandwidth. Yeah, or maybe going deeper. Yeah. In case of wireless communication, we need to be aware about the medium. In wired communication, it's either single-ended, the twisted shielded pair, or fiber solutions. These are the options we have, and of course they differ a bit in case of capabilities. So we can have higher throughput in fiber, lower in single-ended non-shielded cable. But the differences were, to be honest, not really great. Besides, if we have two cables, if we have three cables, so even on one PCB, we can have two UARTs, three SPIs, and Ethernet, and they can coexist easily on one PCB. In case of wireless communication, it's of course not the issue. In case of wireless connectivity, we have the medium, the electromagnetic medium around us, that is useful from tens of kilohertz, let's say, in case of electromagnetic medium, maybe maybe lower than this, but this is usually it's for data transfer is not very useful as the data transfer is very slow at lower frequencies. But from hundreds of kilohertz to today 10 megahertz, even 60 today, there are some communication interfaces working at such a high frequency. So we have theoretically a lot of bands to play with, because there is a lot of frequencies in the electromagnetic spectrum, but naturally the truth is that the frequency that we are able to use, that we are allowed to use, able is one thing, but that we are allowed to use is much more limited. It's much more limited from the electromagnetic spectrum. So I've got, let me find the slide. Okay. Now, here is the useful range, the electromagnetic spectrum that we have around us. In fact, from our point of view, we are able to go from here to more or less here, above 10 gigahertz. We are talking about the radar, mostly radar solutions. But even here, the problem is that we are not allowed to use any frequency from the we are not because there are so many possible users that are possible customers that it's difficult to find a slot, to be honest. So this is the frequency allocation examples in case of the bands. Here in this example, we've got so here it's not, you can see it, but this is 3 mega, this is 30 mega, 300 mega. So these are the decades, 30 giga and 300 giga. So this is the useful frequency range, and there are various colors showing military, police, the government, and various other bandwidths. And what is left for us to use for communication, for the wireless communications, are basically 4 bands. They are basically 4 frequency bands. Yeah, who knows? Maybe do you know the bands that we can use for the communication, for the data, and which are used in data communication today? There are 4 bands. Who knows? Maybe any of the bands. Where is the data transfer going on today? In which bands? Frequency bands. Nobody? Really? Are you there? The first useful band from practical point of view is 433 in Europe. Second is 868 in Europe, again, because it's different in different parts of the world. In US, it's 915, for example. Then we've got 2.4 gigahertz. This is the major band where major of data transfer is going on, and as well 5 giga for some Wi-Fi, applications. Only those bands are available, and because of this, we are moving back towards maybe this diagram. Because of this, on the market appeared a couple of ideas how to utilize the data, how to make the data transfer in those limited, more or less, bands. And again, some of these ideas were standardized. Some of those ideas are just proprietary, so they are just used by in some special cases, in some equipment, by some manufacturers. It depends. So from a practical point of view, we can classify those interfaces as depending on the range and depending on the bitrate. So we have wireless personal area interfaces, wireless metropolitan area interfaces, wireless wide area networks, so interfaces. From the bit rate, yeah, they are in bits per second. It's low rate, is medium rate, and we can classify them as high rate interfaces. So then sometimes we can find in the those letters combined together to form a low rate wireless personal area network. For example, there's some networks are there fitting into various criteria. From practical point of view, out of those tens, hundreds of various options, because they are I have it somewhere. Yeah, for example, here the options like N+, like wireless M-Bus, like Z-Wave, and like wireless HART. From those options on the market prevail just a few. So the most important interface, there are just the few most important interfaces. So we've got the interfaces that are basic on the 802.15.4 standard. These are the low rate personal area to metropolitan, personal area to local area, because there should be here wireless LAN as well. So that the range to tens of meters. Then we have the interfaces based on the Bluetooth itself, so 802.15.1. Which have higher data rates. The range is, to be honest, similar. So basically the Bluetooth is somewhere there. Then we've got the Wi-Fi from those three interfaces, popular ones, with much higher bitrate, and of course the range, which goes up to tens of meters. And then we've got the short interfaces like here, like LoRa interface, like the LoRa one, and here we've got the interfaces like NFC. Interfaces. So these are the free of charge options that we have today. So working in non-licensed bands, because for example the WiMAX, which you have here, so 802.16 requires licensed bands. So these are and that's not popular in embedded systems. It's an access network. From embedded systems point of view, LoRa, NFC, Zigbee, Bluetooth, Wi-Fi, these are the options that we are using today. And from the license band, LTE. From license band, the LTE itself, the LTE unfortunately requires more. 5G, because well, if we talk about the fifth generation of the network and fourth generation, the problem is that they are both the interfaces we can use today in microcontrollers. We can try to use the data transfer on 2G, 3G, 4G, and or 5G mobile networks. The problem with mobile networking is that it's licensed, which means that we need to pay for it. So of course, with today we're going towards beyond this 5 gigahertz, and you mentioned about the FR2 being above 24 gigahertz. I know it is. So there is the Wi-Fi 802.15, 802.11 AD, which is specified or even up to 60 gigahertz. There is a lot of bandwidth at 60 gigahertz. But try to design electronics at this frequency range. You will see how problematic it is, and it's still not evolving in the way that I would like it to work, to evolve. I would like it to work. So these are the options we have today in case of microcontrollers. We will start, but not today because it's almost a break. So we will start. I will try to show you the options we have from a microcontroller's point of view, especially the options that we have already included as peripherals, because we can always use modules. So this 4G, 5G, Wi-Fi 802.11, and for example, it's a fantastic option delivering us hundreds of megabits per second theoretically, but it's not present in any microcontroller up to my knowledge. But the options like 802.15.4, 802.15.1, like LoRa, these are the options which we have included. NFC, which we can easily build in because it's not such a complex interface that it cannot be built, cannot be integrated into a microcontroller, even if there is a peripheral block missing. For this reason, during this lecture, we will just focus, let's say. We'll just analyze this part of the diagram, this part of the chart. That's why we will focus only on the interfaces which are present as peripherals inside microcontrollers. So the interfaces which get out, which don't fulfill this feature, this point, will not be included in the analysis. Anyway, thanks for today. So today we are just almost at the break, so no sense of starting anything new. So we'll get back to the description, comparison of these interfaces already after Easter. So happy Easter to all of you, and all the best also for today. Thank you very much for today. See you next time.